we're going to look at several applications of working model 2D that I consider basic so that we can move on to using them for vehicle design. So let's take a look at some of these examples that I have worked out, and let's start on our web page in there. And the first one that I have in mind is the slider mechanism. So what you do is click over here. Let me get myself out of here. And this is what you'll see. Okay, this is what you would see in here. So let's get this. We have a mechanism that is composed of this 4-bar linkage. One of those 4-bar linkages is the slider here. You can see a slider right there. And then we have this cranking here with the motor in here. So if we run this, this is what we'll see here. And what is important here is to have you realize that what we're doing is getting and collecting some very important piece of information, and that is the force on the pin joint here. And what it allows us to, the plot that you are seeing being formed, I'm just going to stop it for a moment here. It indicates the components of the force in the x direction and the y direction, and of course the modulus, so the value, the total vector velocity, vector force in this case. But these are important because we are able to find out the forces that in the joints. And while this is an exercise so that we can get used to the program, the intent here is to teach you and have you practice the ability of getting the values of the forces in different parts of a mechanism. If you have a steering mechanism, for example, it is very important to be able to analyze these forces, because on the steering linkage, you have these terminals, you have these ball joints, and to be able to design those and design them for durability, and you need to know what forces you're talking about. And we are going one step beyond just calculating the forces in one position, because working model 2D has the ability to do that in different positions. See, right now we made a run, but I could move it back to any position that I want. See in here, I could just make it to different positions in here and see how it changed. Now you know that we can do the same thing for the center of mass of the linkages or any other part that we want. Because, for example, in here we'll say, define the vectors. No, first of all, we need to select a linkage, and if we say define vectors, we're gonna define, let's say let's define the acceleration vector, yeah. And I am going to, when we do that for a linkage, let's do it for this one too. Okay, I'm just gonna define the acceleration vector, and that is here. If you do that, guess what happens? See, those green vectors that you have in there, and you see it here, are the ones indicating the direction and magnitude of the acceleration of those points. But needless to say, I was going to say reset, if we measure the acceleration in here, if we imagine the acceleration, we can have we'll just say alt here. See, this is the acceleration on here. Let's move over here. So it's going to give us the numbers, but also if you do that, here we go, measure the acceleration in here. If I get another one, I can actually make it plot or give me the numbers. So we have enough for the numbers in here, but I would like to see them on the plot in here. See if we can do that. There we go. So we are looking at the measure of the acceleration of the center of mass of this. See? So you can get some very useful information for this. For example, just for the sake of example, let's put this in the horizontal position. The acceleration will have to go to the right at some point. I'm trying to see if it shows in a visual way. Yeah, see here it goes to the right because it has the normal acceleration at that particular point. But if you move it a little bit more, either forwards or backwards, the acceleration has a different direction. See? And so the same thing is true for this one. So I just want to let you know that you can do all these things once you have this. So let's go on to a different one. So you can download this, all this. This is another simulation that I have. And you can also download this. Let's take a look at this one. Okay, this is an interesting one. Although you may appear boring if we look at this more than 15 seconds or so. And you may say, Professor, what are you trying to show us with this? I'm trying to show you several things. First of all, the ability to get out the working model to the direction of the velocity of the center of mass. You see how it goes down, and when it goes up, vector goes up. At some point, it cannot go further up, goes to 0, and then it goes down. But also, we have another interesting situation here, and that is that there's total conservation of energy here. And what I'm doing here is studying also the so-called coefficient of restitution. The coefficient of restitution has to do when you have objects collide. And how can you get a plot or on a system like this that would totally conserve energy, and not only that, it would perform this oscillation forever and ever. Absolutely no loss, you see? Isn't that cool? We could do it on the computer when in real life, even the fact that there's air around, sooner or later is going to produce damping and energy would be lost. Not here, so far we haven't lost one. And we'll reset and say, let's click over here. Do you see what this is? of all the properties of the material, mass, and everything, in here, there's the coefficient of restitution set to 1. The coefficient of restitution set to 1 means totally elastic collation. Coefficient of restitution set to 0 means totally plastic collation. I think everybody has taken a basic dynamics class where these concepts are portrayed, but just to refresh your memory, in here, if you have a totally elastic collision, you will have a bounce to the same position and velocity as before. But in order for this to occur, not only this has coefficient of restitution 1, but the ground too. Well, this would have to be a very hard surface like ice or so, or concrete or something that would not absorb or damp the motion, which is very difficult, but that is the principle. If we make either the ground or the object different than this, let's say I go to 0.5 here, and I have set it differently here, coefficient of restitution, and now I run this, guess what's gonna happen? It's gonna die off. See there? In fact, it did. Quick. It didn't stop and reset. It didn't do very much. This, I have the simulation for a long time, and in reality, we could do it simulation for what do we have? Maybe 10. See what happens now? Let's see, we see, or we even could do it smaller. It goes to maybe, no, in 3 seconds it's done. So let's just do 3. See, there you go. See what happens if you run it. See the black dot is an indication of how it bounced until it stops. Yeah. If I don't stop it, the simulation will continue like this. But if I don't do it this way, I set it to the value of 1, you saw how it bounced, but maybe it wasn't so clear. So I would just try this again. And in here, this is elastic, which I think we set it like this. You can see it a little better here. See here? There you go. I think this is much better. See how it bounces? Exactly to the same height. Yeah. It's totally conserving. If you set the ground now, if you set the ground not to 1, but let's see this, you have to 0.6 or so. Watch what's gonna happen. Immediately we have loss of energy, and that's what we will see. Why is this important? I'll tell you why. We are not only concerned in designing vehicles for the sake of having a nice ride and just good performance and everything. But you as the engineer need to think about what happens if somebody gets in an accident. Isn't it true? Huh? If somebody gets in an accident and rolls over, you will have exactly this situation. You will have to consider whether the vehicle rolled in the collisions as the car roll and stop. Are they elastic, non-elastic? In real life, obviously, the cars get smashed. And when the cars get smashed and there's deformation, there's energy lost. How much of it is? Huh? So I'm just gonna give this object an angular velocity and then just pretend that this rolls over, you know, with an initial velocity. In this case, we're gonna go to the right with 1 radian per second. Let's see what it does. Not good enough. So I think we're going to increase it by 5 here. Okay, let's see what it does. So now you see this is as if we would roll over. But you see, what are we looking for in here? What are we doing with this? You see at the beginning of this dissipation of energy, there is some bouncing and then less bouncing and then it finally stops. But think about it, when the car rolls over and hits that pavement, you know, God forgive that it falls on the driver because chances are he may not survive or completely be paralyzed or some very, very bad head injuries and things like that. But if you have that the first impact on the ground produces such a loss of energy in such a way that the car keeps some sort of a decent shape, it's going to deform, but also that the driver doesn't get squished. Because you could see that with a coefficient of restitution of about 0.5 or 6, you know, in 3 seconds, this is over. In about 3 seconds, a person be killed or be severely injured. And it's a very short time for all these events to happen. But you have to understand that the design of the roof of the vehicle and the design of the structure of the vehicle has to be such as to, it doesn't matter what happens to the vehicle, it matters what happens to the passengers. I think it's fair to say that many manufacturers, and particularly European ones, make an emphasis on safety. For example, a Volvo is designed that the car will deform, but not you. All right. So let's go on with this with these other examples that we have in here. So we have in here, I have a square block which would simulate more the vehicle in here. Or this one is to study the kind of forces that that will be produced with this setting in here. This also could, you could see a very not only passenger vehicles but other kind of vehicles like the rides on an amusement park. This is another application where you actually have to know the forces. But we have a couple of sliders, and in this case also no friction, so this motion will continue forever. What is interesting here is that You can see how the forces could rapidly change as it moves, and also how the direction of those forces changes from totally the opposite direction uh, to just changing the magnitude. See? So, any case, it's gonna go stop and reset this one. Let's take a look at um, other example which is more relevant to this, to our study. This is the solution of the windshield wipers mechanism. And again, in this is important to have the values of the forces, you see, the forces that actually produce that are produced by the motion. All these are obtained with the same principles that I told you a little while ago, and this is the way we'll calculate the forces on the junctions. So this is the perhaps is closer to the applications that we want to do for vehicles. We not only have this kind of mechanism, but the suspension systems are also another one. We also have the steering mechanism, several mechanisms that are important. You don't think about it too much, but the acceleration on the engine and the linkages that actually control the amount of gas that goes into the engine are a whole set of mechanisms, very complex three-dimensional mechanisms that also can be studied this way. So let's just make a pause in here and before we go on.